First of all, I would like to thank Suleyman Demirel University for inviting me in such an interesting conference, 17th International Conference on Electronics, Computers, and Computations. In fact, I am very proud to be here with you, and I hope to speak a little bit about one issue, which is called the impact of quantum computing on computer and engineering. And I'll try to give some basic introduction and a history for such an interesting subject. And I'm trying to do my best in order to share with you what is the latest in such a topic. Quantum computing nowadays became one of the important issues that have impact on different area and different subject. For example, when we speak about quantum computer, we speak about the huge power of a superposition, a principle which exists in a quantum, and we cannot find the same issue in classical. So just let us imagine that we have as an atomic system, and we have a very different probabilities rather than binary system 0 and 1 in classical computer. So let us start from beginning and why quantum mechanics important to speak about that. Quantum mechanics is the fundamental theory in mathematics and physics and describes the behavior of matter and energy at the smallest scale, such as atom and subatom, molecules, and so on. Also, it's important because it provides a framework for understanding a wide range of phenomena, including the behavior of material, the properties of chemical reaction, and the function of electronic devices. Additionally, quantum mechanics has led to the development of technologies such as a laser, transistor, MRI machines, which have transformed modern society. Then there is a huge impact on science and engineering come from understanding the basic fundamental of quantum mechanics. Let us go to history. History, it's amazing to see how quantum mechanics and such a beautiful theory add to the humanity. For example, in 1932, a Nobel Prize in Physics was awarded to Heisenberg for his development of the principle of quantum mechanics, which underlines the operation of a quantum computer. And we go in 1965, Richard Feynman. Richard Feynman was awarded Nobel Prize also in physics for his contribution to development of a quantum electrodynamics. Feynman was also one of the first researchers in the world to propose the idea of using quantum computing to simulate quantum system. In 1981, he proposed the concept of quantum computing in his interesting talk in California Institute of Technology. Then, let us go to 1982. Wilson was awarded also Nobel Prize in Physics for his work on renormalization group, which is a technique that is used to study phase transition quantum system. This work has been important for understanding the behavior of quantum system, which is crucial for the development of quantum computing. And he opened up so many opportunities to understand or better understanding of quantum phenomena. In 1985, David Deutsch at the University of Oxford developed the first quantum algorithm. And then in 1994, Peter Shor developed a quantum algorithm for factoring a large number, which is important for cryptography. And he also adds some new directions to understand the use of a quantum in the real world, especially in computers. In 1996, the first experimental realization of quantum computer was achieved by physicists at Los Alamos National Laboratory. In 1990s to early 2000s, several companies, including IBM and D-Wave System, began developing commercial quantum computer, which is a big transfer, a big shift from a classical to quantum. And 2011, Google announced that it had developed a quantum computer that could solve a specific problem faster than classical computer. And a real application started to be in a real life. In 2016, we have announcement for a cloud-based quantum computing platform that allowed users to experiment with quantum algorithms. In 2019, Google announced that it had achieved the quantum supremacy by performing calculation on a quantum computer that would have taken the world faster. Supercomputer 10,000 years to complete. Supremacy is some amazing development has been achieved by Google in 2022. This is a big event. There is Aspect and Glauser and Zelinger. They get a Nobel Prize for a joint work for their experiment which entangled photon, establishing the violation of Billing qualities and pioneering quantum formation science. They started to use quantum entanglement as a power phenomena in order to have a powerful quantum computer. And they got Nobel Prize, which means that the quantum theory and as a quantum phenomena add a large number of Nobel Prize winners because the idea is not usual. And there is a large number of discoveries still yet not achieved or not known. So let us speak about the applications. Quantum cryptography system, for example, when we speak about a quantum cryptography, then we speak about a high security, a very high security, rather than classical security, because here in between a sender and receiver, there is a wave, and if anyone even drops in between, try to get information, the message will be destroyed. So it's more secure than classical one. Let us go to the basic, how to clarify the idea behind the quantum computer. For example, when we speak about the atom, the basic atom, if we have only one electron and a single electron here, and we have the atom we call a ground state an excited state. The first excited state is one, second, third, and so on. When we give energy, then excitation, it will happen. And as such excitation means that we move from 0 to 1, if we speak corresponding to classical phenomena. But we have a superposition. Superposition between 0 and 1, we have a large number of probabilities. For example, when we consider the field contain one mode only, or one color, we call it kit N. Kit N, one mode, means that we have N photons in this field. If we have more than one color, we have two colors, for example, we call it N1, N2, and we call it two mode. And when we have an interaction between atom and field, for example, when we have atom in excited state and the electron excited state, and the field contains N photons, when the interaction happens, the electron will go down, and then we have one photon will be emitted in order to increase the number of photons to be N plus 1, and the system will be in ground state. For example, like this one. So it's come. Electron come down, and there is M plus 1 and G, the system. This is case 1. Case 2, if in a ground state, and the field comes, then the electron will goes up, and we should observe one photon, so it will be N minus 1 and E, this case 2. Then atom, the interaction between an atom and the field like this one. Here is a case of, for example, a qubit, what we call a qubit, quantum bits. The bits in classical 0 and 1, here qubits, quantum bits, contain all these possibilities. So we have here a 3-dimension, and each one has some different values. For example, we have also the superconducting box. Here's a normal reservoir, normal island, and we have a tunnel here, and the electron goes from here to there, which is belong to the 0 and 1. What is interesting here when we consider superconducting? Superconducting materials has a unique properties, because the electron goes through the channel here 2 by 2, not 1 by 1. So the island is connected to the normal reservoir through the tunnel junction and coupled to the gate voltage source. The gate, when we change the gate here, we change the transfer from one side to the other side. And also we can consider a multi-qubit system in order to have a processor for the computer. So just we have some numerical results to plot here the entropy, which is the measure of entanglement against the scale time t and the detuning. And it seems that when we increase the time, we have more oscillations here if the detuning is 0. Once we increase the detuning, we have the entropy equal to 0, which is once, for example, in terms of lambda, it will be 0, and in this case, we have a purity. Corresponding to the atomic inversion, we have what we call its collapse revival phenomena here. And also, when we consider, again, it's the decay, lambda t and k over lambda, this is a decay. When we increase the decay, the linear entropy increase in such a way. Also here, when we consider the relation between a K over lambda against lambda t, we have such behavior. In this case, when we consider what we call its concurrence, we have two phenomena at the same time in such a system. When we plot the concurrence against the scale time and a K over lambda, we have what we call it here sudden burst entanglement. And then we have here, this is sudden death equal to zero here, and then sudden burst once more, and so on, which is a nice phenomena to have in such system. In order to measure the classicality of a system, we plot what we call its Wigner function. And Wigner function, again, is the different value of K over lambda. And we have interesting here, when we have a K over lambda equal to 0, we have a more negative than when we increase K over lambda. And we consider a superposition case in order to study the effect of the parameter theta also on different values. And here also a general case when we consider a Wigner function in such a behavior. When we increase the number of modes, we have a large number of oscillations also on Wigner functions. The same case, but when we consider the detuning equal to 0, also when we consider in MR quantum formation processing, this system, which is a typically molecule used in, for QIB, there are 3 useful nuclei for realizing qubits. They are a proton H and 2 carbons, certain C. The molecule is labeled, which means that the nuclei are carefully chosen isotopes. In this case, normally predominant isotope of carbon 12C as benzene nucleus. Also in NMR, this is the case of NMR experiment. And this is the final, and I hope that I can answer any question. If you have any question, please feel free to ask. Thank you so much. Thank you.